Okay, thanks to the organizers. And yeah, so I'll talk about some way to look at two-layers neural networks that was developed over the last year, and I think it's interesting. Okay, so what is the setting here? We have data YIXI, so that are IID with some common distribution P that is a probability distribution on R. So this is a response variable. This is a feature vector. So this is R times RD. This will be the dimension of the feature vector. And for me, a two-layers neural network will be the following function, parameterized by theta, is just an average of n neurons or n hidden units, and I'll write this as x theta I. Okay, and okay, here the parameters of the networks are these theta i's, and these are organized in a vector theta 1, theta n, and each of these is in capital D dimension. And of course, so overall you have n times capital D, capital N times capital D parameters. And of course, the standard example that we have in mind is the one in which sigma x theta I is a coefficient times a scalar function applied to an affine function of the features. So in this case, theta I is equal to Wi, which is a d-dimensional vector, Ai, which is a scalar, and Bi, which is a scalar. Okay? So generally, capital D doesn't need to be the dimension of the feature space, but will be very similar to the dimension of the feature space. Okay, okay, so what we are interested in, what I'll talk about is, okay, we're interested in trying to minimize the population risk. So the population risk, I'll look at square loss. So this will be the expectation over the data of y minus f of x theta, okay, square. Okay. So this is a function in capital N, capital D dimension, and I'm not interested in any algorithm to minimize this, but I'm interested in doing it by SGD. Why? Because everybody does this. So what does this mean for me? You know, I have a number of iteration k for any k less than k bar. Okay. I have a step size sk, and each neuron updates according to the gradient according to one single sample. Okay, so what is the gradient of the loss for sample k is this one. Sk okay, whatever it is, this. Okay, so I look at the loss. I compute the loss on the kth data point. I compute the gradient of the loss. And I move by a step size sk in that direction. And this is the way I update the weight of neuron I. Actually, I make things very simple. That is, for the rest of the talk, I'll fix this to be a constant. The factor 2 is just for simplifying some of the formula, is some small constant. Okay, and okay, in the papers, actually, we look at a slightly more general case, but it's not really important. So this is the setup I'll talk about for the rest of this hour. If there is any question, please, you should tell me now, or otherwise it will be very boring for you. Yeah.
So you have both k and n here. Should I just think of k equals k bar, k overline k equals to n, or?
Okay, so now I'll go into this. Excellent question. So now we have a bunch of parameters. Before I go into the next point, any other question about the setting? Because I'll answer Nati's question in a second. Yeah.
You have small n and capital N.
Yeah, so small n is the number of samples, and capital N is the number of hidden units. So if I had to draw a slide, a funny picture, this is the picture that I would have to draw. This is D, this is N, and then there is one output unit. So this is the network. Okay?
How do you run them? So you run all of those gradient descents simultaneously?
Yeah, this is so all the I are updated at the same time in parallel. I can just remove the index I, but I want to keep the index I because then I'll come back to it.
So just my question was about little if, which is
Yeah,
a simpler question.
yeah.
Okay.
There was another question back.
I'm just a little confused about the notation. So it looks like it says theta I is equal to WI of theta I of BI.
Well, you know, in this specific setting, then the parameter theta I of the ith neuron is formed by three objects: a vector Wi, an offset Bi, and a coefficient Ai.
Okay, so there's like two meanings.
This is
That's an A.
this is an A. Sorry.
Okay. Thank you.
This is a very good point. No, it is. Okay, excellent.
F hat in the expectation is just sum over 1 thing, like what
So f hat is this thing,
in the expectation.
and the expectation is the same thing as I wrote there. And the expectation here is over y and x. It's-
Only 1 theta.
no, yeah, I mean, there is only one theta, but there is all of the vector of theta I. Theta is a vector of vectors, okay? Theta comprises all the parameters. Okay, hopefully everybody's with me now. Okay, now to Nati's, relevant to Nati's questions. Here we have a bunch of parameters, right? So what are the parameters that we have? We have the sample size, we have the number of neurons, we have the dimension, and then we have the number of steps of SGD that we do. Okay, and depending on how do I take the relative size, I'm interested in all of these being large, of course, and depending on which one is larger and what is their relative size, you end up getting different regimes and different behaviors. Okay, and what's happened over the last years is that people started, I think, understanding some of these regimes, and there is not yet a complete picture, but let me at least try to give what is the way I understand the picture as it stands right now.
I'm sorry, my question was maybe more basic, so I'm afraid I'm not understanding.
Yeah. So think of this k bar as the number of each time I take a new data point.
Okay, so this K, when you write the YK,
Yeah.
it's not the same as Y. So you didn't,
Yeah.
is it the K data point? Or because if it's a K data point, they cannot, or is it like Y I of K? Yeah, okay. That was with
I sample one data point from the sample.
So it's
But in the
with
yeah.
replacement for
Yeah.
sampling from the,
Yeah. So each time I take a new data points from the sample. In the end, I'll take the one pass setting, but for the moment it's just I take at each step one sample from my data set. Okay, so these two objects are a priori different. Okay, so now I want to try to give a little bit the idea of what is the landscape here, or the landscape of the theory. Okay, one first regime that one can try to look at is the case in which you only have a few neurons, and the number of data point is of the order or bigger than the number of the dimension, and perhaps the number of steps is much bigger than the number of data points. So each data point is visited many times. And okay, I don't know. Okay, now I'll make up names for these different regimes. I'll call this the small network regimes. Small because you don't have a lot of neurons. And this was studied. It turns out that in this regime you can study in very detail a lot of things, not precisely SGD, but still should give a description of the asymptotic behavior of SGD. And it's been studied using basically spin glass techniques. And in particular, there was a nice paper last year by Aubin et al. So this was at New Rips. Okay, where they use statistical mechanics techniques to understand very precise things about these regimes, and there is an interesting phase transition and an interesting behavior. There is a second regime that has been studied, and this was mentioned in Ron's talk this morning. This is the number of neurons is bigger than the number of data points to some power, and also the number of steps is bigger than the number of some points to some other powers. And here I put the powers C and C prime because it's not really clear what is the optimal power here. Papers have values like 6. And this is, I'll call it the kernel or over-parameterized regime. And this started with a paper really from EPFL by Jacou et al. And then there is this paper by Du et al. That studied the same regime. And what happens is what Ron was describing this morning, that is, in this regime is so over-parameterized that SGD runs for very few steps, and very quickly you converge to very small error. And basically what's happening is that you can linearize the network. What matters is really the linearization of this function around the initialization, and you end up to doing something that is very similar to kernel ridge regression. So this is why I call it the kernel regime, because essentially what you're doing is kernel ridge regression with an initial kernel that is determined by the initialization of the random weights. There is a third regime that has been studied, and this is, we look at n bigger, let's say, than d, and then the number of steps is, let's say, smaller than n and bigger than d. Okay? And again, these things are a little bit trying to oversimplify things, but this is what we call the mean field regime. And it's a regime in which you have a large number of neurons, but you don't do a whole lot of steps. In particular, you visit each data point essentially once. And in fact, the rest of my talk, I will stick to the setting in which each data point is visited just once for simplicity. But things should be generalizable. And this was studied by several groups. So there was, so all of this is 2018, and then Rotkopf, Van den Eyden, and then Bach or Shiza. So this is a regime in which neurons move very little. These weights theta move very little, and you basically linearize the dynamics. This is a regime in which the dynamics is non-linear. Neurons move a lot, but you try to take advantage of the large n to simplify the description. And okay, observation. Okay, so first observation, as we said, each data point visited once. So we'll think of this actually now being k. We have infinitely many data in each one, but still we'll take k potentially much smaller than n times d. Okay, so in a sense, I'm still using much fewer data points than the total number of parameters in my network. Okay. So these three regimes are all interesting. I'll focus on this one for the rest of the talk for the good reason that I don't have a lot of time, and this is the one that I'm most familiar with.
I'm just curious, another regime kind of between these two where n is of the order d, but you make lots of steps, but k bar is
much smaller than.
k bar is much larger.
Yeah, that would be interesting. No, as far as I can tell, not really. All right, so this is, of course, not an exhaustive list. It's just a list of what. It's try of making a mental picture for me, first of all, on what has been done out there. And this, really summarize, these two blackboards summarize perhaps, 20 papers. Okay, so, and it's a very rough summary. Okay, so. So now I focus on this mean field regime, and hereafter, for simplicity, my data distribution will be such that there is a function, there is no noise. So yi is just a function of xi. And this is just for simplicity. And a good point to start is start with the universal approximation. A good starting point for understanding what are the objects up here. So here is this theorem of Barron's that says, okay, it asks, is there a point theta that gives you, that approximate the function f that reproduces the data? And Barrow proves the following. This is less than 1 over n. Okay, where f is the Fourier transform of lowercase f. Okay, so this is in RD. So Barron is saying, okay, there exists a network that can approximate any function f with this object finite and gives you a quantitative bound of what is the number of neurons that you need to achieve that. And notice that this bound depends only on intrinsic properties of the function and doesn't depend explicitly on the direction. And R is the maximum of x, of the norm of the features. Okay, and if you look at the proof of these or similar theorems, what is one way to think about the proof of these theorems? One way to think about that is the following. I have this class of functions. I want to understand which functions can be approximated in this way. And one useful thing is to relax this class of functions to all functions that can be written in this form. After all, this is the average of sigma x over n data points theta I. So it's a special example of this class where rho is a sum of n delta functions. And the first step in these proofs, or a conceptually useful step, is to say, okay, let's relax for a minute things to include any possible probability measure here. And then, once you do that, you say two things. First thing, our special case, n neurons functions corresponds to taking this example. So I said, I recover those class of functions if I restrict rho to be of this form, just a sum of n delta functions, of course. And then I can say I do two things. I say any function can be represented as, let's say, star, where star is this formula. All right? So first you show that any function can be represented in this way, and this is very similar to Fourier analysis. This is a Fourier coefficient, and you are taking the Fourier transform of the measure. And second, you say, well, any rho can be approximated by n Diracs. And of course, all of this is very sloppy and very informal and must be made precise. But one way to think about it is that, okay, here I show that I can get f by taking some measure. Then what I'll do is that I'll approximate this measure as just a sum of n delta function if n is very large. then will be a good approximation. For instance, you can center this delta function at IID samples from rho. And by some sort of law of large numbers, this rho n will converge to rho. Okay? So if you think about this way, now what you want to understand, this theory tells you about representation. What you want to understand is about which networks are learned by stochastic gradient descent. It is natural to ask the following question: can we study the evolution of this density, of this distribution? So I look at k steps of SGD, and I look at the empirical distribution of the data points, of the neurons. Okay, so now I should stop and should ask if there is question, because this is the key object that we try to study. So again, you will be very bored if you don't get what is this. This is I'm running SGD for k steps, and then look at the histograms of my neurons. Each neuron is characterized by a d-dimensional vector. I look at the histogram of these neurons, and I try to study the evolution of this object. There is something very natural about it, in the sense that, as Rong was saying this morning, this network has an annoying features that these neurons are exchangeable. You can permute it, and nothing changes. So this means that representing it as a vector of this type is, using a very redundant representation, because if you flip two of these, you get the same network. Instead, this is the natural way to represent the network, because this is, independent, invariant under permutation. So you are factored away the permutation, so it's the right way to think about these networks. Okay, so can we write an evolution for this probability distribution? And the answer, so how does this evolve? And what we would like to do is write some kind of ordinary differential equation for the evolution of this object. And the answer is yes, there is a way to write the evolution of this. And this is a partial differential equation, because now we lifted to the space of probability measure. So this is an infinite dimensional space. We need to have an evolution in an infinite dimensional space. This is a PD. And the PD is this one. OK, I'll write it for you. OK, there are many ways of writing. This is just my favorite way. Where this V of theta OK, so what I want to do, so this is the PD. It is a bit scary, I confess it. But what I want to try to do in the rest of the presentation is try to clarify in what way this is a good approximation, in what sense in which regime this is a good approximation for this. And second, what is the meaning of this and what you can do with it. And hopefully by the end of the hour, you will get some intuition out of it. Okay? But this is something that you start with the rho 0, and you can evolve, and the time derivative of rho is this one. Yeah, there was a question.
So are you assuming any stochasticity between this expression?
No. So the
Like the order matters, right?
here, any no, there is no, I'm taking the example, apart from the IID, the samples are now IID because I have many less steps than the number of samples, so the samples are now IID, so this is random. But once we take the limit, so now I'll take a limit and show that in a certain limit, this is approximated by this evolution. And this evolution is a completely deterministic evolution. Now, you can try to go over it, and there are corrections to this that have also been studied, and there are papers about deriving central limit theorem about this. But the way to think about this is that this is really what I'll state. I didn't state anything yet. I didn't give you a theorem yet. But the theorem that I'll give you is the sort of law of large numbers. So you start with an object that is random, and you end up with an object that is deterministic. Okay, so this is a law of large numbers. This is describing the limit, and the theorem that I state is a law of large number that says this converges to this in a limit n going to infinity. Yeah.
I'm also confused about the statisticity again. So you have.
So this
This is a stochastic evolution.
okay, I didn't state anything. Yeah, I didn't state a theorem. So let me perhaps state a theorem. Yeah. Yeah.
Okay.
And as I said, one can study corrections to this, but this, if you do even, so as you see, this uses only population quantities, so it's basically doing gradient throw in the population risk. And the proof, yeah. So this is a limit in which all of those things disappear. So we are reducing things to the bare minimum. Okay, so this is a theorem. Okay, so the theorem says this. Assume that you start now SGD with these parameters that are IID with some distribution. For instance, yeah. Go ahead.
Is the gradient, is that a variational derivative?
No, this is the gradient with respect to theta. And all of these, okay, this is typical. Okay, I didn't know anything about PD before stumbling into this. And I'm doing this the way you do it in PD, which is typically you write formulas that don't make any sense, and then you explain in what sense they don't. This doesn't make any sense because this is in general a measure. And now I'm taking the gradient of a measure. Okay? Think of taking the gradient of a delta function. This is not what you want to do, right? But there is a sense in which this makes sense and means in weak sense. What you say, that is, it makes sense when you integrate this against a test function. Okay? So think that rho is smooth for simplicity. So you start with theta i's that are IID with some distribution. And then we make the following assumption. One, that sigma is bounded, and the gradient of sigma is, so the gradient with respect to theta of sigma is a random variable because x is random. This is C sub Gaussian. So C will be absolute constant. And assumption number 2, okay, and also this assumption y is also bounded. Okay, and assumption number 2 is that v and u have gradients that are bounded and Lipschitz. So these are assumptions. You might like them or might not like them, depending on your favorite model. But then under this assumption, the following happens. Take any window of time, and you look at the soup of time between 0 and t of some distance. OK, we can do it in many distances. Let's say that you do W2. Between the solution of this PD and this empirical distribution, OK, and then t over epsilon. I claim that this will be smaller than e to the some constant times t plus 1 times some error term that depends on n, d, and epsilon, and the same for the risk. Okay? And so in this, okay, this depends also on a parameter zeta. Okay, this with probability bigger or equal than 1 minus e to the minus zeta z square. Okay? So there exists an error term that I'll write in a minute, such that if you look at the distance between this distribution, which is the solution of this partial differential equation, and the object that I'm interested in, which is the empirical distribution after k step of SGD, this W2 distance is smaller than something that unfortunately explodes with time, but for time of order 1, this is a constant, times an error term, and the error term goes to 0 with n going to infinity and epsilon going to 0. And notice here that you make things match. You have to scale time in the right way. So t time corresponds to t over epsilon time steps. Okay? And okay, this is a distance between probability distributions. It's Wasserstein 2 distance. I don't know. If you don't ask me, I will not tell you what it is, because it doesn't really matter too much. It's a reasonable notion of distance.
If you took s k equals epsilon over 2, you deliver here?
So the 2 appears there. So if you rescale epsilon, you'll get another constant here. Okay, and in fact, in the papers, we use a slightly different scaling, and here you get a scaling that depends on time. Okay, but the 2 is such a way not to get factor 2s here. Okay, so
What's the scaling of epsilon? How does epsilon?
I didn't write you what is this error term. So far I wrote a triviality in reality, because this could be humongous, right?
But how do you think of how epsilon changes as the other parameters increase?
Okay, just one moment. I'll write you the error term, and hopefully this will clarify things, okay? So what is this error term? So this is the error term. All right, so this is the error term. It's something that goes to 0 when n goes to infinity, and goes to 0 when epsilon goes to 0. So both n has to go to infinity. You must have a large number of neurons, and epsilon must go to 0. So you must have a small number, a small step size. Okay? Now, how small have to be? Well, they have to fight this factor. Z doesn't matter. Z is a constant that gives you the probability, the high probability statement. Log don't matter. Actually, I heard first from Piotr the joke, what are a few logs between friends? So I'll use it here. So this doesn't matter. And so what really matters is n has to beat d, and epsilon has to beat d. So the condition for this approximation to be accurate is n has to be bigger than d, or much bigger, which is what I wrote. And epsilon has to be much smaller than 1 over d. Okay? Notice that if you take a generic dynamics, you would expect that this kind of ODE approximation is accurate when the step size is smaller than the number of parameters. So what's surprising here is that what shows up is the dimension is not the number of parameters. So the naive thing would have been 1 over nd here. Instead, here what shows up is 1 over d. Okay? Because the number of parameters in my network is n times d. But the step size only has to be smaller than 1 over d. Okay, so now that's this. So Perhaps I'll give you an example. So think of the following example. Think that this thing converges in a time, the PD converges in a time of order 1 to a good position, to a good global configuration. Then how many samples did you use? When the number of samples that you used is capital T over epsilon, which is order D. Okay, so you only use a number of samples that is order D, which is much smaller than the number of parameters that is n times D. So this is surprising somehow. And the other surprising thing is this, and this also shows if you add noise to the model, the approximation are always in the terms of the dimension and not in the number of parameters. So this makes you think that there is something in this approximation that is non-trivial. OK, so let's see what time it is. OK, so now I have 20 minutes, and I did 1/4 of what I... So I want to do something crazy, that is try to explain how you prove this, not because I want to brag about it, because it's not so difficult a proof. It's because I think the proof brings out what is the intuition behind this thing. And the proof goes in 2 steps. Step number 1, or you can think about 2 steps. You approximate SGD by gradient flow on population risk. And step number 2 is the approximation, the gradient flow on population risk by this PD. OK, so I will not belabor on point 1. I'll just write what is gradient flow on the population risk. Let's see, where did I write SGD? All right, so if you remember what was, so step number 1, so if you do this, then you get this approximation. So for step number 1, I say very little, because it's more standard. What is SGD doing? Let me rewrite what I wrote before. Is this theta ik plus epsilon. If you take the gradient of the loss, you get sigma. And then OK, so this I just rewrote, and I did the exercise of computing the gradient of a square. And what does it mean doing this approximation? Means, first of all, replacing this by its expectation, because I'm making many steps, and so many steps will average out. And you can effectively replace this by its expectation. Technically, you do by some standard martingale concentration. And then you replace the finite difference by an ODE. And at the end of the day, you get this kind of evolution. The derivative with respect to time of this, when you rescale time, is equal to minus gradient of v of theta I minus 1 sum over j gradient over theta I of u theta I theta j. So this is a motion, continuum motion of n particle corresponding to n. Each of these particles try to minimize this v, that is, tries to fit as well as possible the data. So each neuron is trying to fit the data. But then they interact, and in fact, they repel each other through this term. And this makes sense, because you don't want two neurons to be too close, because this will mean that you are kind of redundant. OK, so this is the continuous. So this is really the gradient flow in the population risk, is this n-particle dynamics. And this, in going in going from this to this, really what you use is not n large, you only use epsilon small. The second step is this one, so I want to spend a little bit more time on this. I can rewrite this. If you look at it, this is very similar to this object here. The first term, the gradient of this object. The first term is the gradient of this term, and the other is the gradient of this term when rho is replaced by the empirical distribution. So one way that is very convenient to rewrite this is that you are writing theta I dot equal minus gradient of psi theta I rho at n t, well, this rho at n t is just 1 over n and now we want to connect this guy to that partial differential equation. And the way this is done is the key insights is what's called the nonlinear dynamics, or one way to do it. By the way, this type of proofs have a long history in mathematical physics because people were interested in system of particles, and this kind of technique can be traced back to the Brushin, probably in the 50s or 60s. And the basic idea is the following. What is the nonlinear dynamics? Is the following problem. You look at a single particle now that evolves according to this. So suppose that you are given, you see, this is a particle that moves in the force field given by the other particle. And here I'm doing the same, except that this is fixed and given externally, and chosen in such a way that this is equal to the law of theta t. All right, so let me stop for a moment and tell you how you should read this, because I want to teach something. So think that you start with some conjectured evolution of this density of particle, rho t. You plug it in here. Now you have a single particle that evolves in the force field determined by the others, right? So this is given, and now you have an ordinary differential equation for your single particle theta. This evolves in the force field. Now you compute the law of your single particle theta. This is the law of your single particle theta. Okay? And you say that something is a solution of the nonlinear dynamics if it's a fixed point of this process. So I start with a rho, then I get a theta, and then I compute a rho, and I want this to be equal to this. All right, so easy lemma. So this is very nice, because easy lemma, rho is a solution of this if and only if it's a solution of this partial differential equation. So actually these two things are two completely equivalent ways to look at the same things. All right? So equivalent to PD. And it's very nice because it gives you a really concrete probabilistic interpretation of this analytical object. In particular, it's an easy way to prove existence and uniqueness. Okay. Okay. Now we have two objects, this guy and this guy. These are two distinct objects. But we wrote them very similar. This is rule number one of how to find a proof. You have to prove that A is equal to B. You try to write in the A and B in such a way that look as similar as possible. Here we wrote this particle dynamics in this form, and you wrote this PD in this form. Now they look very similar, except that this is a law of a single particle. This is a law of n interacting particles. What you do is the following. You just do a coupling, a very simple coupling. So you put the two processes on the same space. How? Well, we said that the initialization are these I at the rho. And now what I do, I run n of these processes. So let me put a bar here just to distinguish from the previous ones. OK? So I have this one. This gives rise to this theta it. So this is the evolution of according to the particle dynamics. And then I start n independent with the same initialization. So the difference is that these are independent and these are not independent. Okay? But okay, now they live on the same probability space, and what you do is that you bound the distance. So for instance, you bound this distance. Okay, so you bound the distance around time. This is kind of, you just write write some kind of ordinary inequality for the derivative with respect to time of that object, and you see how it evolves. Okay, so this is somehow the sketch of the proof. I didn't do the details, but hopefully I conveyed the idea that this PD here is describing the evolution of a particle in the force field created by the density of all the other particles. Okay, so it effectively reduces a problem that is n times d-dimensional to a problem that is d-dimensional. Okay. Any question about this? Yeah. What is the advantage of thinking in terms of, I'll give you a few examples in a second. All right, so this is, so, oh. Sorry? Do I use the PD? No. But I use the, the fact that basically this mapping is a contraction in the space of rows. But so far I haven't used it, but so I only prove that this holds in the limit. Right?
I'm still a bit confused where the magic came from. So intuitively, you would think that you would need epsilon to be like 1 over nd in order for this to exist.
Right.
And I don't understand how. I mean, you said that several times, but I still don't understand how. Where's the magic hiding that you only have that epsilon 1 equals 1 over d?
Well, the point is that these things interact in a very specific way, right? This guy depends on the evolution of this guy. So if this was given, then it would be d the relevant factor. Now, what we prove is basically is that this is not given. This is a random thing, but concentrate very well around a deterministic object. So even if it's not given, it's as if it was given.
Okay, so I guess it's hiding in this when you say concentrate very well. I mean, you have to quantify.
Right.
Okay, so it's not that we. Okay, so there's still some magic. I'm just trying to find out where is the spot where that.
Yeah, but I mean. Yeah, I mean, but it's related to the fact that the nature of, the concentration is very much related to the fact that the nature here of the dependence on the other j is exchangeable. You see, this guy is not whatever function of the other j. It's a sum of functions of the other j's.
Okay, so you're down from.
Okay, read the proof and I don't know, the magic somewhere. I mean, yeah, okay, so there is a point in which we prove concentration of this, and this is the, what obviously I didn't talk about, and is the crux of the matter, of course. Okay. I mean, once you prove that this empirical distribution concentrates, of course, this is done, right? Yeah. Okay, so I want to spend a few minutes at least talking about what you can do with this. And one thing you might want to do is, of course, try to prove some approximate global convergence. So Rong this morning was talking about how do you prove that SGD or gradient descent converges to a global minimum, and he gave kind of a philosophy about it, and the philosophy is more or less you carefully study the landscape and show that it doesn't have local minima in which you can get trapped, right? Here this gives another philosophy, and the philosophy is I will look at this high-level description of the problem, or this that hides away some features. So the original landscape might have local minima that disappear in this limit, and then I kind of try to prove something about the behavior of this trajectory, of this evolution. So in that sense, you'll get approximate global convergence because this will be basically modulo this kind of theorem. So what I mean by this is that strategy that is a two-step strategy. First, prove convergence of R of rho t. So this is at the PDE level. So this is the expectation of f of x minus f of x rho t square. And two, okay, you connect back by use the general theorem. So in several of the papers that I mentioned, another paper, there are theorems of this form. And the general upshot of this theorem is that they give good results for finite D. But the question of the dependence with D is not really settled, or it's not really well understood, I would say. I mean, there are bounds, but not good bounds. So both our paper and the paper by Shizai and Bach and others prove results of this type that hide a little bit the dependence with D. So what I want to do is not going to state this result, but try to explain where the convergence come from and what is the limitation and where the magic come from in analyzing the PDE. Okay? So I think a useful starting point is asking ourselves what are the fixed points of the PDE. So if you look at this infinite dimensional evolution, it will get stuck. It will get stuck in fixed points. So it's a good starting point to try to understand what are the fixed points of this object. And what is a fixed point of that object? Well, if you think about it, you want the right-hand side to be 0. So really what this implies is that this has to be 0. So let me not go into the detail of showing this, but you understand that, of course, if this is 0, then the derivative with respect to time is 0, and vice versa, if the derivative with respect to time is 0, that has to be 0. The converse is not obvious, but it's true. So what does this mean? It means that one of these two pieces is 0, so it means that this is supported when this guy is 0. So the support is of rho. Rho cannot be everywhere 0 because it's a probability distribution. So it must be that the support of rho is inside the set of gradient 0 of psi. So the fixed point are all this distribution rho such that the support is inside the set of theta such that the gradient with respect to theta just let's pause a minute because this is not an obvious equation to parse. You give me a rho. What do I have to check? I have to compute this function psi, computes its gradient 0 point, and it must be that rho is supported. This function psi will be some function like this. Must be that rho is supported on this or on this stationary point. Okay. No, not the minima. Yeah. The stationary point, the 0 gradient points. Okay, so if you're a physicist, this makes sense. I am a physicist. If you're a physicist, this makes sense. This is saying that you have a fluid of particle. It must be that each particle feels 0 force. This is the force that each particle is feeling. Okay. Now, what are the global minima? Okay, so you have this function. This is quadratic in rho. You can, this f hat is linear in rho. So this R is really quadratic of in rho. So you have a function that is quadratic in rho. In fact, it's convex even. And this rho lies in the simplex. It's a probability distribution, so it's non-negative and normalizes to 1. So you can put Lagrange multiplier, etc. You can find out, with a simple exercise, that the global minima are the points such that the support of rho is inside the global minima of psi over theta. All right? So again, it must be true that you compute this function, you look at it as a function of theta, look at the global minima, and rho must be supported this. So in this picture, rho must be supported here. Okay, so this in particular shows that not all the fixed points are local global minima, and actually you can construct counterexamples. But these two equations are not too far, right? So what drives all these proofs of global convergence is the fact that these two conditions are not too different. And let me give you, explain you in what sense they are not too different, at least intuitively. Let's consider a fixed point rho star that is supported everywhere. Okay, why not, right? We have a probability distribution. We assume that this is a well-behaved distribution. It's not supported on a few points. It has a nice density, perhaps. Not necessarily a density, but it's supported everywhere. Why?
It's still in the distribution.
Right. But here now I'm looking at the n to infinity limit. All right. So I forgot, eventually I will use this. No, I have 0 seconds, so I'll be a bit quick here. But eventually I will have to use this theorem to connect to finite n. But for a few minutes, I'm living in an infinite dimensional world in which rho is, Okay, so suppose that you have a fixed point and it's supported everywhere. So what that must mean, it means that the gradient is 0 everywhere. But what this means, it means that psi is a constant. And what it means that every point is the argmin. And what it means that rho star is a global minimum. So if you know that rho star is supported everywhere and is a fixed point, it must be also a global minimum. So if you look now at these proofs, basically, that are in these papers that I mentioned before, basically what you try to do is you try to avoid rho to become degenerate. If you can manage to avoid that rho t at some point become degenerate, so a support concentrates on a few points on a lower dimensional subspace, then you are done. You get global convergence. So this is done in various different ways in the different papers, and I don't have ways to go over it. This also shows you the limitation of this, because these notions of support in large dimension are tricky to deal with. Yeah, perhaps I stop here, because otherwise Piotr gets upset. Yeah.
Questions?
I have a high-level question. The difference between the kernel over parameterized and the mean field. So the way I would have drawn the distinction is not in these parameters little n, big N, and k, more in the size of the initialization. Because there's like over there you had the only difference in your regimes was that you had the k is upper bound, right, for the mean field. But then the PDE holds for any large finite time as long as I have enough particles. So then it seems to me the difference is actually in the initialization state, in that in mean field, when you initialize, you draw from the same measure rho 0, and you give each neuron mass 1 over n. But in the kernel papers, you give each one mass 1 over square root. Do you have any thoughts?
I don't think that is really a fundamental thing. Actually, I think that you can get the kernel limit even if you do 1 over n, except that, I mean, you can get, okay, I will not go into details of this, but yeah, I'm not sure that is actually the distinction. I think the distinction is really that you will have the overparameterized, for having the overparameterized regime, you must be overparameterized, right? You cannot do it in this setting. This setting is one in which you have more data than steps. So, but okay. So you can get the kernel regime also within this framework by looking at a special case of this framework.
By initializing it.
No, but also by initialize, yeah, slightly different, but it's not the 1 over n versus 1 over square root of n difference. I don't think it's that. Yeah.
Can you point to what the obstacles to more layers come from?
Yeah. I mean, you can try to write something formally, but there is obviously, if you do this for more than one layers, there's going to be, the basic structure here is that entering is basically that these n neurons are exchangeable. This is what we're leveraging at the fundamental level. And if you have exchangeability, for probability theory, that things are going to get easier, right? Now, if you have 2 layers, now there is still an invariance group, but it's much more reduced. So, somehow a more reduced group means that, okay, you can factor out this symmetry and get some simplified description, but since the symmetry group is much more reduced, the description is much more complicated. And you can try to work out what is the description into 2 layers. We also did it, but it's not something particularly, at least, it's not something that we could get any useful result out of, right? But I mean, I think there are some interesting things that can be looked at before this. For instance, this goes more or less true if you have convex loss. I did it for square loss, but for instance, Francis does it for general convex loss. But something already very interesting, I think, would be to look at non-convex, 2 layers with non-convex losses. That is, you can have some interesting things happening. And if you don't understand that case, you will never understand 3 layers.
Very quick question.
Is there a way of understanding how large n has to be for these results?
Yeah, so we have bounds that Okay, there were bounds somewhere written, but under this regularity assumption, we require n that is much bigger than d times a bunch of factors that depends on basically how regular are this function u and v and this sigmoid, etc. Now, one question is, if you look at a specific data set, does this work for n smaller than the upper bound? We did simulations, and both for some synthetic data and some simple real data like NIST, turns out that you can get away with n much smaller than what the bounds give, which is kind of interesting and puzzling because, okay, for a number of reasons. Yeah, okay, so